Hello students, welcome to a series of mathematics program for grades 10 and 11. The topic for today is sequences. This is in fact the third part on sequences. You will recall that in the first lesson, you had learned about the different types of sequences, such as the sequence of triangular numbers, the sequence of prime numbers, the sequence of square numbers, the sequence of cube numbers, arithmetic sequences, where the difference between any two consecutive terms is always the same, and geometric sequences, where the ratio between any two consecutive terms is always the same. In the second lesson, you had learned about the Fibonacci sequence, which is a sequence of numbers in which each successive term is obtained by adding the two previous terms in the sequence. For example, 1, 1, 2, 3, 5. You had also learned about the sequence of ordered pairs, and remember, the sequence of ordered pairs can be compared to coordinates, where we consider the x values as a first set of numbers and the y values as a second set of numbers. And each set of numbers will form its different, separate sequence of numbers. We had also learned how to find the relation between ordered pairs of a sequence. So comparing an ordered pair of sequences to coordinates, for example here, we will have x value as 2, the y value as y, and if we want to find the relationship which exists between x and y, we need to consider the values. So here 1, 3, so 1 times 3, 2, 6, 2 times 3, 3, 9, 3 times 3, and so on. So we can say that y equal to 3x. In today's lesson, we will learn about how to continue a given number sequence, how to recognize patterns in sequences and relationships between different sequences, and how to generalize sequences as simple algebraic statements, but more specifically for the Pascal's triangle and for number patterns from patterns of figures. So let us start with the Pascal's triangle. Look at this diagram. This is the Pascal's triangle. In fact, the Pascal's triangle was originally developed by the ancient Chinese, but Blaise Pascal was the first person to discover the importance of all the different patterns it contained. So, observe this diagram. What do you notice? As I have mentioned, you have different rows, row 1, row 2, and so on. You also have different diagonals. This is diagonal 1, diagonal 2, diagonal 3, and so on. So try to observe the diagram and try to come up with different patterns which exist in this diagram. So if you look at the first diagonal, it consists only of ones. So remember we had repeating patterns, so I can consider this as a repeating pattern, 1, 1, 1. If we look at the second diagonal, we have 1, 2, 3, 4, 5, and so on. These are what we call the counting numbers. Now, if you look at the third diagonal, 1, 3, 6, 10, and so on, these are the triangular numbers. Now, consider the first row, we have number 1. Second row, we have 1, 1. Third row, 1, 2, 1, and so on. Now, the first row, we have number 1, which is also 11 to the power 0. The second row, we have 1, 1. That is 11, which is 11 to the power of 1. The third row, we have the numbers 1, 2, 1, which is also 121, and it is equal to 11 to the power of 2. Similarly, for the fourth row, we will have 11 to the power of 3, which is equal to 1331. So you can see that in Pascal's triangle, we have many different patterns. There are a few more patterns which I haven't shown you yet, but which will be found in the exercises. We now move on to number patterns from patterns of figures. So in this part, you will be given a set of figures and you will have to identify the rule which is making the figure change. Let us consider these 3 figures: pattern 1, pattern 2, and pattern 3. What do you notice? You can see that in the first pattern, we have 1 square. In the second pattern, we have 2 squares. In the third one, we have 3 squares. So in the fourth pattern, how many squares will we have? Yes, we will have 4 squares. Similarly, we can continue the pattern in the 10th pattern. For example, pattern 10, we will have 10 squares. Now, if instead of considering the number of squares, we decide to consider the number of sticks. So in pattern 1, I have 4 sticks. Pattern 2, 7 sticks. Pattern 3, 10 sticks. What can you observe in this column? 4, 7, 10. We are adding 3 to get the next term. So in pattern 4, we will have 10 plus 3, that is 13 sticks. And in pattern 5, I will have 16 sticks. Now we are going to consider this example. So consider the following pattern of counters. Part A, we need to complete the table. And then we have a few other questions. So part A, I need to consider this pattern of counters and I have to complete the table. So you can see that in pattern 1, we have 6 counters. In pattern 2, we have 10 counters. Now, what about pattern 3? Can you count how many counters we have in pattern 3? Yes, we have 14 counters. Now, look at the number of counters. The row number of counters. We have 6, 10, 14. So we are adding 4 to get the next term. Now for pattern 4, we will have 18 counters. For pattern 5, we will have 22 counters because we need to add 4. Now the second part, part B. The number of counters needed to make pattern n is kn plus 2. Find the value of k. So we shall use the table from part A. You can consider pattern 1 or pattern 2 or any of the other patterns to find the value. Here we have considered pattern 1. So n is equal to 1 and the number of counters is 6. So I will have k times 1 using this expression kn plus 2. I will have k times 1, pattern 1, plus 2 equal to 6 because we have 6 counters. So k will be equal to 4. Now part C. There are 700 counters. Ami uses as many of these counters as she can to make one pattern. Given that this is pattern P, find the value of P and find how many counters are not used. So for pattern P, we will have 4P plus 2 because remember K is equal to 4. So 4P plus 2 will be equal to 700. Now I need to find the value of P. So P will be equal to 174.5. Is it possible? Can I have a pattern number 174.5? No. So P is going to be equal to 174 because the pattern number should be an integer. It should be a whole number. I cannot consider 175 because I will be using more than 700 counters and Ami has only 700 counters. Is that okay? So we consider P as 174. Now we need to find how many counters are not used. When P equal to 174, the number of counters which are used will be 4 times 174 plus 2. That is 698. So number of counters which are not used will be 700 minus 698, which is 2. Second example. Patterns are made of sticks as shown in the figures. Part A, you need to draw pattern 5. Part B, you need to complete the table. And you have 3 other parts. So let us have a look at the solution. These are the patterns given. You need to draw pattern 5 for part A. So I will have to add a square below. As you can see, here you have 1 square and a triangle, 2 squares and a triangle, 3 squares and a triangle. So for pattern 5, I will have 4 squares and a triangle. Part B, I have to copy and complete the table. So pattern 1 makes use of 6 sticks. Pattern 2, 9 sticks. Pattern 3, 12 sticks. Now for pattern 4 and 5, how many sticks will be used? So again, I try to find a pattern by considering the number of sticks used. So 6, 9, 12 will be 15 and 18 because we are adding 3. So which pattern will have 30 sticks? So this is from the previous part. Now to find out which pattern will have 30 sticks, as I mentioned, we are adding 3. So pattern 9 will have 30 sticks. Part D, I need to find an expression for the number of sticks for pattern N. So you will remember that in the first lesson, we had learned about arithmetic sequences. So we are adding the same value to get the next term. We are adding 3. So the first term here is 6 and the common difference is 3. So the number of sticks for pattern n is 6 plus 3 into n minus 1. And simplifying, we will get 3n plus 3. So remember, in arithmetic sequences, we had learned this is the value of a, the first term, and this is the common difference. So number of sticks for pattern n is 3n plus 3. Now part C. And so otherwise, find how many sticks are needed to make pattern 200. So number of sticks needed to make pattern n is 3n plus 3. So to make pattern 200, I replace n by 200 and I get 603. Now you have a few questions to practice on number patterns as well as on Pascal's triangle. So for example, here we have a following pattern: 1 to the square minus 0 to the square equal to 1, 2 to the square minus 1 to the square equal to 3, and so on. And you have to write down the 8th and 9th line, and so on. This is question 3. Question 4. And question 5 here. And you have one question on the Pascal's triangle. As I had mentioned earlier, there were a few more patterns which we hadn't discussed, and you will have to discover these patterns in this question. So students, we have reached the end of today's video on sequences, where we have learned about the Pascal's triangle and the number patterns from patterns of figures. This is the last video in the series of videos on sequences. I hope you have enjoyed the videos and you have also understood the different concepts, the different types of sequences. So until we meet again, it's goodbye from me. Thank you for your attention.